Okay, so in the last class we defined compact operators. Let's continue to discuss that. So let H be, we deal with separable Hilbert spaces. Okay. You can deal with non-separable Hilbert spaces also, but you will not encounter much. And the other thing is this will be very similar, except you have to use nets and deal with uncountable, orthonormal basis with uncountable cardinality. That's all. The Hilbert space. Okay. Then we define this finite rank operators. So this means range is finite. Okay. Range is finite dimensional. This is, then we proved that this is a star two-sided ideal. Two-sided star ideal. Ideal containing in this B of H is a ring. Okay, it's an algebra. It's a vector space as well as a ring. So in that ring, it's an ideal. Okay. So then we define K of H equal to the closure of F of H in the norm topology. Okay, in B of H. So this is the closure in norm topology. We showed that if you take a different topology called strong topology, which is point-wise convergence, this is uniform convergence. Norm topology is uniform convergence over open balls, over balls, closed balls or open ball, whatever. It's uniform convergence over bounded sets. Okay, bounded sets in Hilbert space. If you use just point-wise convergence, then this K of H is dense in B of H, if you take that topology. But if you take the topology of uniform, if you take the norm convergence, then it is just a proper ideal. That's what you will show. In fact, this will be the only closed ideal. This finite rank operator is an ideal, but that's not closed. So we will not prove that, but it will follow that the compact operators, the algebra of compact operators, which does not contain identity, it's not non-unitary algebra. That's a only closed ideal contained in B of H. There is no other ideal. Okay. So only norm closed ideal. So this is how we defined compact operator. And it's easy to see that this is also a, so if T is in K of H, so K of H. Okay, then T star is also in K of H. Okay. That is because if Tn contained in finite rank operators and Tn converges to T in norm preserves the norm convergence, and because norm T star is same as norm T. So because of the Tn star will converge to T star in norm. Okay. So because of that, this is star closed. And also if Tn converges to T, then Stn converges to St and Tns converges to Ts. So these things implies that this K of H is a two-sided star ideal. This is also a two-sided star ideal. Okay. Contained in B of H. Okay, this is an ideal and it's a two-sided ideal and it's also star closed. And as I said, it's only closed ideal. Okay, now let us see some properties of this and our equivalent conditions of this compactness. And why is this compactness is there? What is compact about it? So that's what we will see here. So proposition. The following are equivalent. Following conditions are equivalent for an operator for T in B of H. So one is T is compact. That is, it's that's in the closure of finite rank operators. See, the thing is how much there are some properties of operators, basically matrices on finite dimensional Hilbert spaces, finite dimensional vector spaces. So they have some of the properties, and how much we can take those properties. Something like, I mean, it takes bounded sets to compact set, or it's if it is normal, it is diagonalizable, and how much these properties can be taken over to general operators in Hilbert space. These, even though these compact operators are genuine infinite dimensional operators, they will possess some of the, they will continue to have some of the property. They inherit some of the properties of the finite rank operators. So that's what we want to see. And one of them is for the following. So, I mean, in finite dimensional, weak topology and norm topology coincide. So if something is, if something is norm convergent, we have seen that, I will write it here. We have seen that if T from H to H is norm continuous, if you put norm topology on the domain and range, then T is also weak continuous, in the sense that if you put weak topology on the domain and range, and it's I mean, it's equivalent. We have seen that. But if you put weak topology on the domain and the norm topology on the range, then there is no reason for them to become, for the T to be continuous, given that T is bounded operator. But that will be satisfied by a finite rank operators. So a compact operator will continue to satisfy this. But then for some reason we take only the open balls. So let H1 equal to T restricted to H1, from H1 to H, where H1 equal to unit ball. I mean, you can take any ball, that doesn't matter, is continuous with respect to weak norm topology. Okay, you can put the weak topology on the domain, I mean, which is the ball, and then norm topology in the range, then this is continuous. That is, it takes weakly convergent sequences to norm convergent sequence. So the third thing is, this is equivalent to saying T of H1 is compact. Okay, is compact, right? So that is also equivalent to saying that T of H1 is relatively compact. I don't want to write that. So this is also equivalent to saying, but then the unit ball, see, I have given an assignment. The unit ball of Hilbert spaces are reflexive. That's what Ries lemma says. So the dual, I mean, in fact, the dual of Hilbert spaces can be identified with the Hilbert space itself with the slight changes. I mean, there is it's not isomorphic, it's anti-isomorphic. And the dual of the Hilbert space and the double dual is same, of course. There is an isomorphism between the Hilbert space and its double dual. So it's reflexive. So when it is reflexive, weak topology and weak star topology coincides. So in particular, the unit ball of the Hilbert space is weakly compact. So this will imply that T of so T of H1, it will follow from that. It will, I mean, 2 to 3 is trivial. That's what I'm saying. Anyway, we will see in the proof. T of H1 is compact. This is also equivalent to saying, no, I wanted to say something else. So in particular, the H1, the unit ball is weak star compact, and I have given an assignment that the unit ball is, unit ball is metrizable with respect to weak star topology. Here, the weak topology and weak star topologies are same. So the H1 is metrizable with respect to the weak star topology. So because of that, the compactness will imply sequentially compact. That's what I want to say. Okay. I mean, I have given the proof orally. Okay. So if X1 contained in H1, okay, then there exists a subsequence X and K such that T of X and K converges. Okay, that is what sequentially compact means. Every sequence has a convergent subsequence. So Tx and K converges. Okay. So these are the equivalent conditions which I want to prove. So 1 implies 2. So what does 1 says? 1 says T is compact. That is, it's in the closure of finite rank operators. Then T restricted to H1 is continuous with respect to weak norm topology. So that is, we want to prove, we assume that T is compact. Let T be K of H, T is compact. Then we want to prove that it is continuous with respect to weak topology. In the domain we put the weak topology, and in the range we put the norm topology. So suppose Xn is a sequence which is contained in H1 in the unit ball, and Xn converges to X weakly. Okay. Then Txn we want to prove the following. Then we want to prove Txn converges to X in norm. Okay. That's what we want to do. It's continuous with respect to weak norm topology. Weak topology in the domain and norm topology in the range. Okay. So what is given? It is given that T is compact. Okay. It's a compact operator. T is a compact operator. That is, T can be written as a limit of a sequence of finite rank operators. Okay. So in particular, we can say that there exists a S in finite rank operators. So S is a finite rank operator, range of S is finite, such that norm T minus S is less than epsilon. Okay. So we can choose an S like that. Okay. So now we want to prove that Txn converges to X in norm. So we want to consider this Txn converges to Tx, not T, not X. So this can be written as Txn minus Sxn, right? Plus Sxn minus Sx plus Sx minus Tx, right? So this is less than or equal to, this is equal to 2 times, less than or equal to, okay, less than or equal to 2 times T minus S. And we have that norm Xn is in the unit ball. So norm Xn is less than or equal to 1. So I just remove this 2x plus Sx. These two I have clubbed, this and this. Okay, clubbed together, and I will turn it as 2 times T minus S, and then Sx minus Sxn minus Sx. Is this fine? Okay. I hope everything is fine. So Sxn minus X. Okay. So we have to show that this goes to, so now this is less than epsilon, 2 times epsilon plus Sxn minus Sx. So all we have to show that Sxn minus Sx goes to 0 as Xn goes to X weakly. Now Xn goes to X weakly. Okay. S is bounded. S is finite rank operator. So in particular, it is bounded. It's a bounded operator. So S is from H to H is norm continuous. So this implies S from H to H is weak continuous. This we showed in the last class. Okay. If you put weak topology in H, and if you put weak topology in both sides of H, domain and range, then this is continuous. Okay. So this particular Xn converges to X weakly. This implies Xn converges to Sx weakly. Okay. But S of H is finite dimensional. Right? So this implies Sxn converges to Sx in norm. So this you have to see if you take any finite dimensional subspace or finite dimensional space, then the weak convergence there will imply, I mean, the weak convergence and norm convergence are same. What does it mean if you have a finite dimensional? If H is finite dimensional, okay. What does it mean? There exists a En, a basis n equal to 1 to n or something contained in H is a basis, is an orthonormal basis. Okay. Then Xn converges to X weakly is equivalent to saying Xn Ek converges to Xek for all k. But then this is what is called coordinate convergence. In finite dimensional, coordinate convergence is equivalent to saying that Xn actually convergence in norm. Okay, please verify that this implies Xn converges to Xn. Okay, so because of the range of S is finite dimensional, this Sxn converges to Sx weakly will imply it converges in norm. So now we have this equation. We have only Sx minus n. This will go to 0. This will go to 0 since this. I mean, so these things implies Txn minus Tx is less than or equal to epsilon 2 epsilon plus Sxn minus x goes to 0. Okay. Okay, so 1 implies 2 is proved. Okay. Is this fine? We can ask any question. So these are the 4 things. So T is compact operator, then T is continuous with respect to weak norm topology, and then we want to prove T of H1 is compact. That is clear. 2 implies 3. That is because H1 is weakly compact by Banach-Alaoglu theorem. Okay. I don't know. I'm not able to write it out. Banach-Alaoglu theorem. H1 is weakly compact. So because T is continuous with respect to weak topology and norm topology, T of H1 is norm compact. Okay, norm compact. So that's what I want to say. So 2 implies 3 is fine. And 3 implies 4 is just, I mean, it just says that T of H1 is compact. So if you have any Xn contained in H1, then that is, then T of Xn is compact, right? T of Xn is contained in a compact. So it will have a subsequence which converges. So 3 implies 4 is just, there is nothing. It's just the property of compactness. 3 implies 4. This is true since H1 is metrizable. If H is separable. I mean, if it is not separable, then the same thing will true for nets. Okay, every net will have a convergence subnet. I mean, every net will have a subnet such that T of that subnet will converge. Okay. So then you can, I mean, we want to prove 4 implies 1. For that, this will, I mean, we will use this. Now we want to prove 4 implies 1. So what is 4? Every 4 says the following. For every sequence in the unit ball, there is a subsequence such that T of Xn, T of that subsequence converges in norm. Okay. So from that, we want to prove that, assuming that we want to prove that T is compact. That is, it is a limit of finite rank operators. Okay. Okay. So we have already seen this kind of argument earlier, that finite rank operators are strongly dense in B of H. So we are going to use the same thing, except that strong, I mean, see, what is the difference between strong convergence and norm convergence? Strong convergence is point-wise convergence. Some Tn converges to T, strong convergence if Tnx converges to Tx. Norm convergence means that convergence should be uniform over balls. Okay. So that is what we want to prove here. Okay. So assume 4. Okay. So assume 4. 4 says that suppose every xn contained in H1, there is a subsequence, has subsequence. Actually, we can take the sequence itself. Okay, anyway, so the statement is written, I do not write it. So every xn has a subsequence such that T of xn converges. From this, we want to produce a finite rank operator, sequence of finite rank operators, which converges to this T. So let T be, suppose T satisfies. Okay, let's. So we assume 4. We want to produce T. So let this we have already seen. Let En is an orthonormal basis for H. Okay. Then you define n equal to 1 to infinity. Then let Pn equal to projection onto span of finitely many of them, E1 up to En. Okay. Okay. So then Pn is finite rank. Right. So this implies P and T is also finite rank. And we claim that P and T converges to T in norm. We have assumed the property 4. That is, every sequence has a subsequence such that T of that subsequence converges in norm. So assuming that, we want to prove this. Okay. So P and T will converge to T strongly, that we have already seen. For I mean, that is P and Tx will converge to Tx. Okay, for all x in H. But we want P and T. I mean, this convergence should be uniform. We want this convergence to be uniform. Okay. So why is this true? Okay, suppose this does not happen. Suppose, I mean, P and Tx converges to Tx, we have seen last one in the last class. Okay. Suppose P and Tx does not converge in norm to T. Okay, that is, the convergence is not uniform. That means you can't choose a n. I mean, what is convergence? Given epsilon, you have to choose a capital N such that for all any small n greater than that n, the difference between the Tx minus P and Tx should be less than epsilon. And that n you should be able to choose for all x in H1 uniformly, so that you cannot choose uniformly. So that's what this means. Suppose it does not converge uniformly. So that means there exists an epsilon naught. Okay. I mean, for any given epsilon, you should be able to choose as n. So the negation of the statement is there exists an epsilon naught such that for all n, we will not be able, I mean, we will not be able to choose a n for each x. So there exists an epsilon naught greater than 0. And yeah, and for all n, I mean, this is a standard argument. For all n, there exists a n, there exists a xn. I mean, it basically says there is a subsequence which satisfies something. So I want to say the following. The claim is, I mean, this says for all epsilon naught, the see you have to given epsilon naught, there exists a n you have to show. That is for all n. There exists for all n. There exists a n greater than n such that t pnt xn, there exists a n such that pnt xn minus and xn. Okay. I mean, this should happen for all x, no? So, and xn in H1 such that pntxn minus txn is greater than the epsilon naught. Okay? This is the negation of the statement. So, this thing implies there exists a sequence. In particular, there exists a sequence xn. Okay, this is a sequence in the H1 such that pntxn minus txn is greater than epsilon naught for all n. Okay. Is this fine? This is somehow hiding this. Can you see this? Can you see the screen properly?
Yes.
I was not able to see. Yeah. One second, I will just move this. I mean the participant, no, that is hiding the what I have written, at least in my screen. I don't know whether it is okay in your screen. Okay. So this argument is okay. Can anyone say yes?
Yeah, it's fine.
Fine. Okay. So given, I mean, there exists a subsequence. There exists a sequence such that this happens. Okay. Now the property we are assuming is the property 4, which says that if you have any sequence, there exists a subsequence such that T of xn converges in norm. So without loss of generality, I mean, we can by going through a subsequence if needed, without loss of generality. I don't want to write this. We can go through a subsequence without loss of generality. We can assume Txn converges to y in norm, some y. Okay, for some y, and it should be in H1, of course. No, it need not be in H1, in H. It is just in the, it's in the range of H1, T of H1, so which is something. Okay, so T of xn convergence in now, conversion now. So now we want to get a contradiction. That's all. Now what do we have? We have epsilon naught is less than or equal to Pn Txn minus Txn. Okay. So I want to use the triangle inequality. So this just implies that 1 minus. So I want to. So which is just equal to 1 minus P times T Txn. So this is less than or equal to 1 minus P times T of xn minus y plus yeah, and then Txn, so 1 minus P y. Is right? I mean Pn. Right? But there is some confusion here. Is there a confusion? See, there is this n coming in Pn and there is a n coming in the subsequence. They may be different, but that's okay. I mean, those n's may be different. Actually, we can just fix a P such that it is close enough to identity by that's not correct. No, this is okay. This is okay. I mean, you can take a subsequence and then get a Pn. Okay, please go through the argument. It will be okay. 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 Now, So this, I mean, Pn is projection, 1 minus Pn is also projection. So 1 minus Pn is norm is less than or equal to 1. So this is less than or equal to Txn minus y times 1 minus Pn times y. We know that this goes to 0. Okay, they both goes to 0. Pn, I mean, Pny goes to y for in norm for all y. Okay, that's what you have proved. And because of this goes to 0. But it's greater than epsilon naught is a contradiction. Okay, is a contradiction. So, which is a contradiction. So this implies 1. This implies P and T converges to T in. Okay. So if you have any problem, tell me. You can tell me later also.
Y should be outside the T, right? The previous line.
What is this?
In the previous line. First application of triangle inequality. Should
Y
be T of Xn minus
we should be outside the P. What did you say? I'm sorry, I didn't hear.
the first term in the triangle inequality. T of Xn minus y.
Here.
Yeah.
Here. In the next line.
Next.
Next line. 1 second, I'll erase that. The next line, 1 minus Pn, T, Xn minus y. And then you want this what should be outside?
So 1 minus Pn is distributed T of Xn minus. Oh, sorry.
No. T of Xn, oh, sorry. No, this should be outside. Correct. You are right. T of Xn 1 minus. No, T of Xn. Okay, this should be outside. This bracket should not be there. Let me write it.
Yeah.
1 minus Pn into T of Xn minus y. Right. This is bad. It's not Ty, it should be y. Right. Txn converges to y.
Yes.
That's now it's fine. Correct. Good. That's all. So we have proved. We have proved the proposition. Okay. So everything is clearly written except my handwriting, which is okay, which is not very bad. Okay. So please go through it. If you have any problem, you tell me. Okay. So this basically, so this is why it's called compact operator, because it takes bounded. I mean, a bounded operator takes a bounded sets to bounded sets. A compact operator takes bounded sets to compact sets. Okay. Okay. So that's why it's called compact operator. Okay. Okay. Now what is the next thing? What do you want to do next? So okay, now so this is something we have seen, it carries over the properties of finite rank operators. Now in finite dimensional, we know that any matrix, if it is normal, okay, in finite dimensional, so this proposition is over. So in finite dimension, if you have a T in B of H, which is a matrix, of course, then if T is normal, if T star T equal to T star, if it is normal, then it is diagonalizable. Diagonalizable means what? There exists a orthonormal basis En contained in H n equal to 1 to some n, such that Ten equal to lambda n en. So there exists a set of eigenvectors and eigenvalues such that T can be written like this. I mean, that eigenvectors span H. Okay. Or in other words, if you have a matrix, if T is a finite dimension, if T is an MNC, is normal. I mean, matrix means we are just writing it with respect to some particular basis. Okay. T is an abstract operator means you are not writing with respect to particular matrix. Particular basis. So here you are fixing a basis. Then that means that there is a unitary U in MNC such that UT, U star is diagonal. It's a diagonal matrix. Okay. So diagonal matrix, I mean, it's just the diagonal matrix, with zeros everywhere except diagonals. So that, I mean, that's what unitary means. Unitary is something which takes orthonormal basis to orthonormal basis. I mean, if you are given two orthonormal bases, there is a unique unitary between them. Okay, the unitary is defined by that. I mean, it is exactly the columns. If you fix a standard orthonormal basis, and you write the matrix with respect to that standard orthonormal basis, and if you take any other orthonormal basis, then you just write those orthonormal bases as column vectors. Okay, and that is precisely the unitary. And if you, I mean, you should have seen it in linear algebra or in the what Shruti did. If you go through those things, it will be clear. Okay. So It is just this UT U star. So if you have the matrix with respect to standard orthonormal basis, then there exists another orthonormal basis with respect. I mean, this is UT U star is just writing that matrix with respect to some other orthonormal basis, and it is a diagonal matrix with respect to it. And that is precisely means that it has eigenvalues lambda n with respect to, I mean, with En as eigenvectors. Okay. So this theorem can be carried over to compact normal operators. Of course, if the operator is compact and it's a purely infinite dimensional, the H is infinite dimensional, then compact operators can be infinite dimensional. And then this theorem can be taken through. And that is what we call it as the spectral theorem for compact normal operator. And that's what we want to prove now. Okay. So before proving it, let us consider there is some condition for compactness. So that condition we will prove now. So T is in B of H. Now H is not finite dimensional. Okay, H can be infinite dimensional. We'll let H be any separable Hilbert space. Okay, and T in B of H is said to be diagonalizable or diagonal operator. Is diagonal operator. This is definition. Is diagonal operator if it has eigenvectors and eigenvalues and the eigenvectors span H. If there exists orthonormal basis En contained in H, orthonormal basis such that T of En equal to lambda n En. I mean, this is the definition of eigenvector. Okay, so I don't want to go through that. This I think everybody knows. In finite dimensional spectrum and eigenvalues are same thing. Infinite dimension, that's not the case. It's because in finite dimensional, invertibility is equivalent to saying it's injective. I mean, it's 1-1. I mean, when T H is, I mean, operators from H to H, it's from the same Hilbert space to same Hilbert space. Then injectivity is same as invertibility. In infinite dimensional, that's not the case. It may not be onto. Okay, so because of that, in the eigenvalues need not be same as something in the spectrum. Okay. So here we are talking about eigenvalues. Something is diagonalizable or it's a diagonal operator if there exists eigenvectors. There exists eigenvectors or orthonormal basis. It's a corresponding eigenvalues. That's what we call as diagonal operator. Okay. Okay. Now the proposition. Let T in B of H be diagonal operator. Diagonal operator with eigenvalues lambda n. Okay. I mean, corresponding to En, which I am not writing. Okay. Then T is compact if and only if lambda n goes to 0. So this is the condition for compactness. Incidentally, notice that a diagonal operator need not be bounded. You can define a diagonal operator. If it is bounded, it's equivalent to saying. So this is exercise. Sorry, can I put a space here? Yeah. Exercise, or I will tell you orally. You just do this. This is not assignment, just exercise. A diagonal operator. I mean, you can define any operator. If you take any orthonormal basis and you have a sequence lambda n, then you can define an operator like this. But then you can, I mean, by defining it, and then you can extend it to the span of En, just span, not closure. But you may not be able to extend to the whole of it. For that, you need its boundedness. If it is a bounded operator, we can extend. Okay, so a diagonal. What do you want to say? I mean, we are assuming it's bounded. So what I want to say is the following: if given lambda n, okay, n equal to 1 to 20, which are complex numbers, and En orthonormal basis in H, okay, we can define Ten equal to lambda n En. Okay. Then T extends to B of H if and only if lambda n is bounded. There exists n such that lambda n is bounded for R. Okay. Okay. And it is clear. If lambda n's are bounded, see lambda. So first of all, if we have some bounded operator which is diagonal, then lambda n has to be bounded because these ENs are contained in the unit ball. So I mean, if a bounded operator, over the unit ball, the Tx should be bounded. Because of that, it will be bounded. On the other hand, if these lambda n's are bounded, then any x can be expanded in terms of this orthonormal basis. Then you will find that it is something like this. If you have an x, then you can write it like xen, en. Okay. Then Tx will be summation lambda n xen en. Okay. Now, if you consider the norm of Tx, that will be summation over, I mean, norm, then norm Tx square will be summation mod lambda n square xen square, right? That will be the norm. Okay. Okay. And then that will be less than or equal to mod lambda n, supremum of lambda n. If you have some that m or whatever that m, then summation xen square. But this is equal to norm m times norm x square. So it is bounded. Okay. So Tx is bounded. I have given the proof. Okay. It's an exercise, but I have given the proof. Okay. So we have boundedness of this x, lambda n. Lambda n is a sequence in small L infinity. So we want to prove that it's in C0. It's a sequence converging to 0. That's what we want to prove. So there is something in the chat. We can see. Thank you. It was written long back. Okay. It's only hiding for me, maybe. Something in the screen is getting. I'm not able to move it. Anyway, if it is visible, it's fine. But maybe in the video, it may not come properly. If I go full screen, what will happen? But I don't see where to go. Anyway, let me not check. Leave it. Anyway, I'm sending you the notes so you can look at it. If in the video, if it's not visible, you can look at it. Anyway, so this is what we want to prove. Okay. So what do you want to prove? If you have a diagonal operator, it is compact if and only if lambda n goes to 0. And one way is clear. One way should be clear. That's because we have already seen that for any orthonormal basis, En contained in H is orthonormal basis. So this implies En goes, and we are assuming that it's a diagonal operator. Okay. Then we are proving it. So if we have any orthonormal basis, then En goes to 0 weakly. Okay. And En is contained in the unit ball. So since T is weak, norm continuous, okay, Ten goes to 0 in norm. But then this is equal to lambda n. Okay, this implies lambda n goes to 0. That's all. Okay. Okay, so now we want to prove the other way. So one way is easy. We want to prove the other way. So other way, we assume the T is a diagonal operator, and we assume lambda n goes to 0. Then we want to prove T is a compact operator. So to prove that T is compact operator, we have to prove that T can be approximated by finite rank operators. So let En be the eigenvectors, orthonormal eigenvector, I mean O and B and eigenvectors. For T, okay. Then what? Yeah. So given choose so given epsilon greater than 0. So okay, so it's enough to show that given epsilon, we have to find a finite rank operator, which is a epsilon close in norm to this T. So given epsilon greater than 0, okay. So we have assumed that lambda n goes to 0. Okay, that's what we are assuming. Then we want to prove that T is compact. Given epsilon greater than 0, there exists a n, and after that, this is less than the whatever we consider, that's less than this. So this set is finite. Okay, given epsilon greater than 0, this set n all n such that or n such that lambda n mod lambda n greater than or equal to epsilon is finite. Yeah. Right? That's what it means. This is a finite set. Okay. Call the set as n, Sn. Okay. And Pn, yeah, there is no Sn. This should be S epsilon, sorry. Okay. Now P epsilon is projection onto En, n in S epsilon. Okay. Which is a finite rank projection. Because that set is finite, this is a finite rank projection. Okay. Now we consider this T minus P epsilon T. Okay. Times some x. I mean, we want to approximate this uniformly. We want to show that this is less than or equal to epsilon times x norm x uniformly. Okay. This, right. So this is equal to what? What is it? What is this equal to? Tx minus P epsilon Tx, right? This is just equal to exactly equal to maybe norm square. I mean, whenever we consider this, we have in Hilbert space, we have to take norm square. Okay, this is equal to summation. So this is, I mean, let me write it again. So it will be more clear if I write it like this. One minus P epsilon times Tx, right? Square. This is equal to summation n in, that is greater than that, no? That's right. N in Sn S epsilon complement, right? Right. S epsilon complement Tx En. Is clear? You can expand Tx with respect to the orthonormal basis. Okay. And 1 minus P epsilon will kill everything in P epsilon. There are finitely many of them. So something in that S epsilon complement will remain. I mean, the indexing set is all n. And then whatever which is not in S epsilon complement, you will get this. This is fine. You can do it by choosing a n and first n or something. That also you can do. Okay. Is fine. If it is not fine, you tell me. Okay. So this is equal to summation n in S epsilon complement norm of mod of Tx En. So mod of Txen square, but that is equal to nn s epsilon complement. I am getting something else. Yeah, that is equal to lambda n xen square, right? Okay. Now this lambda n's are less than epsilon in this set, right? I mean, in S epsilon, it's greater than epsilon. Now in this set, it's less than epsilon. That's the definition of this S epsilon, right? So because of that, this is less than or equal to epsilon square times norm xen square, but you can take the sum from n equal to, I mean, whole natural number, and that is equal to norm x square. Okay, so that's we have got this. So this implies so this implies norm t minus p epsilon t is less than epsilon. That's what we want. Given epsilon is arbitrary. Given epsilon, we want to find a finite rank operator which approximates in norm with the, I mean, with the epsilon closure. Okay? The proposition is proved. So if it is a diagonal operator with an eigenvalues lambda n, then it converges to, I mean, then it is compact if and only if lambda n converges to 0. Yeah, any question? So this is about diagonal operator. Now we want to go to the spectral theorem. But will I have time for this? No, I may not have time for this. I mean, I would better prove it together. I don't want to stop it in the middle. So I will stop today. If you have a question, you ask me. I will do I mean, we have a lot of time, so it's okay. So next week, next class, I will do this. Okay. So we have seen that. So now we want to prove the following. We want to prove that if you have any compact operator, which is also normal, then there exist eigenvectors and eigenvalues. And of course, eigenvalues will converge to 0 by this condition, if it is lambda n. So you want to prove that any compact normal operator can be diagonalizable and the eigenvalues will go to 0. So that's what we want to prove. And we will do it in the next class. Okay. Maybe I will prove one lemma. Okay, lemma. What is a lemma? T is compact operator. Okay. Then there exists an eigenvalue lambda for T such that mod lambda is equal to norm T. Okay. Proof. So first to define a function. Let me claim. I don't want to write the function or something. X going to T xx. Okay. Is this a function? Yeah. This function is continuous. This is in complex number, right? And this is in H1. Is continuous with respect to weak topology. Okay. So X is in unit ball. This is a function defined on unit ball, taking values in complex numbers. And this function is continuous with respect to weak topology. That is, if Xn converges to, since weak topology is metrizable on the unit ball, we can take sequence. Xn converges to Xn weakly. Okay. Then Txn Xn converges weakly. Sorry, in, I mean, this is just complex numbers. They converges. That's what we want to prove. So that follows due to the following. But this is a compact operator. Okay, we have, so anyway, I will write it. So we want to Txn Xn minus Txx. Okay. This is less than or equal to Txn minus tx xn. Okay. So I will get a xn here. I will get a txn, tx xn there, which I will write it here. Yeah. Tx xn minus x. Right. This is okay. Triangle inequality. Triangle inequality, I'm adding and subtracting in different parts of the inner product. Okay. I've just added minus tx xn. So that will appear that I have taken it down there. Okay. Okay. Now we know that xn converges to x weakly. Txn converges to txn norm because it's a compact operator. So this is less than or equal to norm txn minus tx, and xn has norm less than or equal to 1. So you can write it like this. And then this is just tx into xn minus x. Okay. Both goes to 0. I mean, this is goes to 0 since t is compact. And this is just goes to 0 is just the definition of weak convergence. Okay. That's just the definition of weak convergence. Okay. So this is true. So this function is weakly continuous. Okay. It's going to be 430. Okay. So now I want to use this to prove the following. So this function is continuous. So since H1 is weakly compact, I mean, it's a compact metric space. So there exists a x in H1 such that supremum of mod txx, okay, x in H1 equal to tx, maybe call it x naught, x naught, x naught. Okay. The supremum is attained. Should I put a mod there? Maybe I put a mod there. I mean, it's equal to mod of that. That's fine. Mod of this. Yeah, mod is fine. I mean, I take mod. That's okay. Okay. Now, here I need a lemma. I will prove it in the next class. Okay. Lemma. I forgot. T is a normal, compact normal operator. It's not just compact operator. And T is normal. I mean, this is true only for normal operator. I mean, if it's not normal, we cannot make all these statements, all these eigenvalues, all these things. Okay. So it's a normal. T contain, this is true not for compact operator, any operator it's true, is normal. Okay. Then norm T is equal to supremum of x in H1 txx. Okay. See, usually if for any operator, norm T is supremum of norm Tx, which is also same as supremum of norm Txy. Okay. I mean, it will be usually it's like this. Norm T equal to supremum of x in H1 norm Tx. Okay. But if you apply the linear functional, that's also same as supremum of x in H1 and supremum of y in H1, something like this, Txy. Okay. But that is equal to, you can take this y to be x itself. You can take the supremum over x itself. So that is what is true for normal operator. Okay. So this I will prove in the next class. So if the lemma is proved, it will be proved in next class. Proof next class. Okay, so if the lemma is proved, then so we are having, so what we have done. So let me recall the whole thing. We assume T is a compact operator and T is normal. then we want to prove that T has an eigenvalue lambda such that mod lambda equal to norm T. Okay, that's what we want to prove. So for that, to prove that, we have prove that this function x going to the Txx, that function is continuous with respect to weak topology. Since the unit ball is weak compact, we have a x0 such that supremum of x in H1 Txx that is equal to Tx0 x0. Okay. So we have the following norm T, since it is normal, norm T is equal to Tx0 x0 mod Tx0 x0. But then this is less than or equal to norm T times norm x0 norm x0, right? By Cauchy-Schwarz inequality. Okay? Cauchy-Schwarz inequality. So these things imply that norm this Tx0 x0 is equal to norm T, and this is also equal to norm Tx0 times norm x0. And I don't know whether it is proved for you in the last course when Cauchy-Schwarz inequality is proved. Cauchy-Schwarz inequality, the equality holds if and only if the Tx1 is a linear, it's linearly dependent on the other one. So this is equality holds in Cauchy-Schwarz. I mean, we have this Tx0 x0 is equal to norm Tx0 x0. This means equality holds in Cauchy-Schwarz. Okay, Cauchy-Schwarz inequality. Okay, this implies Tx0 equal to lambda times x0. Do you know this? If you just go through the proof of Cauchy-Schwarz, it will be clear. You will have some quadratic equation, all that, no? So some root has to be equal or something like that. Something will follow immediately. It will be clear. Otherwise, it's not true. If you go through the proof, it will be clear. Okay. So because then now we know. So there exists an eigenvalue. Okay, that's what it means. Now mod lambda is equal to norm T by whatever you have done. So any questions? So if you have questions, you can ask me. I will stop recording.